Hello, everybody, and welcome to another wonderful day of chemistry. So last time we talked about how an electron behaves a little bit more like a wave. And this means that it's impossible to perfectly know where the electron is or how fast it's moving. And we're always going to have a little bit of uncertainty in both. And this means that it's going to move around a confined space very differently. So we're going to be looking at what happens when I confine an electron to a given space. And this is most commonly known as particle in the box, as I put a electron, a particle, in a one-dimensional box. A good way to think about this is having an electron moving back and forth along a wire. And it turns out that the electron can only move back and forth along this wire with very specific frequencies. And these frequencies are going to be determined by the size of the box. So let's go ahead and start with the minimum wavelength. So the minimum wavelength has to be about half of the length of the box. And the reason why is I have to have a node or an area of zero probability at either end of the box. If this probability is non-zero, well, it means that the electron could theoretically get outside of this wire. So it has to stay confined, which means we're immediately limited to some sort of functional form where I've got nodes at either end of the wire. And the minimum wavelength that will do this is half of the length of the box, because that way I have a wave function that goes up and then goes down. If the wavelength is equal to the box, I'll have a node at either end and then one right in the middle. And then you can have any number of integers based on this half wavelength, because this will guarantee that no matter whether I have an even or odd number of nodes, that I'll always have a node at the end of the string. So a good way to kind of think about this in more kind of classical terms is a guitar. So if I go ahead and pluck a string in the guitar string really can't move at the end of the wire because, well, it's stuck in place. And similarly, you go ahead and you put your finger down on the string, limiting the length that can vibrate. Can't really vibrate past your finger if you have a good grip. And what you've done when you grip the guitar string is you've set the length of the wire that can vibrate. And so this means that the string can only produce sounds with frequencies that are some integer of that wavelength. So let's go ahead and say you want to play a middle C. So a middle C has a wavelength of about 132 centimeters, which means that the minimum length you're going to need that string to be is 66 centimeters. So if I want to get a middle C, my string either has to be 66 centimeters or 132 centimeters or about 200 centimeters. If it deviates from that even a little, I'm going to get something that either sounds a little off, a little flat, a little sharp, or just a different sound entirely. Because what we hear when we hear that middle C is a very specific wavelength of sound. And it's also one of the reasons why you can have harmonies, because what you'll end up having is different sounds that will build on each other because there's some integer based on that given wavelength. And we have something very similar in light. We're going to have, or with electron stuck in a particle, or with light, where we have very specific wavelengths that can exist in a given space. However, for the most part, they tend to ignore each other. But again, only very specific sounds or colors, or in this case, energies, can exist within that confined space. So let's go ahead and think about how this kind of relates based on energy. So we've got different, we have different possible vibrational states that can exist of that electron moving back and forth. And so we give these essentially n values. If there are no nodes, we have our first energy level because the electron has to move. And this is called the n=1 state. And then we can have an n=2 and an n=3 each time we have an increasing number of nodes. So the number of nodes of this particle in a box will always be n minus 1. And we can go ahead. And so essentially what ends up happening as n gets larger, our wavelength is going to get progressively smaller. N equals 1, my wavelength is twice the length of the box. N equals 2, my wavelength is the box, and then so on and so forth. And we can actually describe a mathematical function that has a very similar set of properties. It's a sine function, because at 0, the sine function will have 0 amplitude. At L, as long as we have an n pi over L, we're going to have 0 amplitude. Sine functions are a perfect way to describe these electrons moving back and forth, and helps explain why only very certain levels are allowed, because we have to have some integer value of L to make sure that we have that 0 amplitude at either end. Now, what ends up happening, as my n increases, my wavelength decreases, and as my wavelength decreases, the particle is going to have more energy because it's going to have to move faster. And we kind of saw this with our de Broglie wavelengths, but even with the photon. The smaller the wavelength, the more it has to move, the electron has to move to jump past the nodes. And so as our wavelength gets larger, my energy and speed will also increase. And it's possible to calculate the energy of each of these possible confined states using this general equation, where our energy is going to depend upon Planck's constant, which we don't have to worry about because it's a constant, the mass of the particle. In this case, we're looking at an electron. But the two key features here are going to be the energy state, which we give as n, and the length of the box. As the state goes up, the energies get increasingly further and further apart. And as the length of the box increases, the energy levels will become increasingly packed together. So our lowest possible energy state is going to be n. And a good way to think about this is that we've already seen that electrons have to have some momentum. If n is equal to 0, then it wouldn't move at all, and it could be located anywhere, including outside the box. And again, what we're going to see as n increases, the separation of energy states becomes further and further apart. So as a result, we tend to see whenever we confine a particle to a given location, that we're only going to occupy a fairly low number of energy states because they're going to be more or less tightly packed together, and it's going to be harder and harder to get further up this energy well. Now, one of the important things that is worth noting is that this wave function that we've generated to describe the behavior of our particle actually isn't physically observable. It really is just a mathematical function that we can use to get all sorts of information. However, in order to get this information, we have to use some fairly intense calculus properties, which I'll mention briefly next time, but we're going to focus on the key take-home points. But we can use this function to get a lot of useful information. One of the biggest things that we can get is the actual probability density. So the probability density is literally the probability that I'll find the particle, or in this case an electron, at any given point in the box. And we can get this by simply taking the squared of the wave function. So if I have the wave function, I can tell exactly where the particle is. Now, a couple key features I want to comment. With our wave function, it can have both positive or negative amplitude. And this allows for essentially electrons to either cancel out or add together in probability density. When we're talking in probability, however, when we're talking about the probability density, this has to be positive because I can't have a negative probability of finding the electron. Though there is some features that they tend to share. They will tend to share the same peaks. So if I have a maximum of my wave function, that is also going to be where I have a maximum probability. Also, where I have a minimum peak, I'm also going to have a maximum probability in my wave function, really showing that it's the amplitude of the wave function that matters much more than its direction. The other really important thing is the nodes. If I cross 0 in my wave function, that will always be a place where I will not find the electron. I will never find the electron with that wave function at one of these nodes. And this can be very important as we kind of progress and move on to talking about real atomic systems. But again, they do share a lot of those same basic properties, even if you'll notice the shapes differ a little bit. The probability density has a little bit of a sharper shape than the more gentle wave function. And again, this is due to that squared function. Now, one of the really cool things about a particle in a box is we just dealt with this in a single dimension. So an electron existing on a wire moving back and forth. But it turns out that the x direction can be treated as completely independent of the y and z directions. So what we can have is, say, a particle that moves in 2 dimensions, where the electron can move either in the x direction or in the y direction. And what we see here at the top is a wave function that has an n of 1 in the x direction and an n of y in and an n of y of 1 in the y direction. And what this does is it guarantees that I have no nodes in the x or y direction. And from that, we can simply add together the energies of n equals 1 for both directions. So the wave functions will multiply together and the energies can simply add. In the second case, we can have an n of 2 in the x direction, where I'll have a single node in the middle, and an n of 1 in this direction. Now, it is worth noting we have something called a degenerate energy level. This is another way of saying an energy or a wave function with the exact same energy, where it would be an n of 2 in the y direction and an n of 1 in the x direction. So think the same wave function and just rotate it 90 degrees. And then we can also do an n of 2 in the x direction and an n of 2 in the y direction to get a much more complex function where I have a node in either direction. And you can extend this to n's of 3 or 4, and it turns out you can even include this in the z direction. However, this becomes a little bit harder to graph. And big thing I want to focus on is how we get these wave functions in multiple directions is we simply take the wave function in the x direction, the y direction, and the z direction and multiply them together. And again, for the energies, you take the energy in the x direction, y direction, and z direction and add them together. So wave functions are multiplicative, energies are additive. So if I know the energy of each independent direction or each independent movement of freedom, degree of movement, I can find the overall energy. And one of the reasons why this is really important is because next time we're going to be talking about hydrogen atoms. And it turns out that hydrogen atoms don't just exist in 1 dimension or even 2, they work in 3. So we're going to have to figure out a way to describe 3-dimensional electrons and separate out the energies into simpler terms that are much easier to address. Until then, take care.